All right, welcome to another deep dive. You know how this works. You send us the stuff that piques your interest and we kind of sift through it, pull out the really juicy bits so you can feel like you've got a real handle on things, without drowning in information.
Yeah, it's all about those shortcuts to knowledge. This time you've given us a whole treasure trove on something super important for senior Java developers. Interview questions and answers. We're talking a comprehensive guide here and a pretty detailed prep resource.
Yeah, and they're packed with info. So our mission for this deep dive is pretty focused. We want to break down those core Java concepts, object-oriented programming, data structures and algorithms. Can't forget that. And of course, the collection framework, all through the lens of what's going to matter most for senior level roles.
Yeah.
The stuff that'll really make you stand out. So yeah, let's dive right in. You ready to start with the JVM? It's pretty fundamental, wouldn't you say?
Oh, absolutely. I think what's so cool about the JVM is that it's this abstract machine, right? And that abstraction, that's what gives Java its platform independence. Basically, it takes your Java code, compiles it into bytecode, and then the JVM makes sure that bytecode runs on whatever system you're using, no matter the operating system or hardware.
Makes sense. And the sources get into the nitty-gritty of how that actually happens. We've got the class loader subsystem, which basically preps those class files. But it's not just one loader doing everything, is it?
No, not at all. It's a whole system, like a tiered system.
Yeah.
So at the very top, you've got the Bootstrap class loader. This guy's the VIP handling the core Java API classes, the real essentials.
Yeah.
Then there's the extension class loader. This one takes care of the classes in those extension directories. And lastly, we've got the application class loader. This one's all about your specific application, handling the classes on your class path. Think of it like delegating responsibility for loading all these different types of classes.
Got it. So once we've got those classes loaded, we move into the runtime data areas, right? This is where the action really happens. We're talking about the method area, the heap, the Java stacks. Could you give us the quick rundown on how they all work together?
For sure. So the method area, that's like the library. It keeps all the metadata about your loaded classes, the class structure, the method code, that kind of stuff. Then you got the heap. This is the big storage room where all your objects hang out during runtime. And as for the Java stacks, well, imagine each thread gets its very own stack. It's how they keep track of all those method calls. So when a method gets called, boom, a new frame gets pushed onto that thread's stack.
So just to clarify, the heaps for the actual objects and the stacks are for keeping track of the execution flow within each thread.
Exactly. It's all about organization.
And the sources also mention these things called PC registers and native method stacks. They seem a bit more specialized.
Yeah, they are kind of niche. So PC registers, those are program counter registers, and their job is to keep tabs on the current instruction being executed by each thread, keeping things running smoothly. As for the native method stacks, those are specifically for when a thread's running native code. That's code written in other languages, and you usually access that stuff through the JNI, that's the Java native interface. Oh, and let's not forget the execution engine. This is the heart of the JVM, actually running the bytecode. It can use an interpreter, which is like a translator going line by line, or a JIT compiler that's just in time, which translates bytecode into native machine code for a performance boost. And of course, there's a garbage collector. It's the cleanup crew, making sure everything's tidy.
Right, the garbage collector. That's on our list to dig into. And just to round things out, it's cool to think about the native method interface and those native method libraries. That's what lets the JVM chat with the underlying system, a whole world working together to run your Java apps. So should we move on to garbage collection? Everyone loves a clean system.
For sure. I think the beauty of garbage collection is that it's automatic. You don't have to micromanage your memory. When objects are no longer needed, the GC swoops in and frees up that space. It's all about efficiency.
And there are all sorts of different algorithms used for garbage collection. Our sources list quite a few. Serial, parallel, CMS, G1, ZGC, a whole buffet of options.
Mm.
What are some things senior developers consider when choosing which one to use, like beyond just trying to avoid pauses?
Well, it really depends on the specific needs of the application, right? Right. Like, for example, the serial GC. It's the simplest. It just uses a single thread to do the cleanup, but that means it has to pause everything else. Like hitting the pause button on your app, you can start it with the command-XX plus use serial GC. Now, this is fine for simpler apps, maybe something single-threaded, or if you're working with smaller heaps where those little pauses aren't a big deal. But if you need more horsepower, there's the parallel GC. This guy uses multiple threads, especially for the young generation collection. It really improves throughput, especially on systems with multiple cores. But, it still has to pause everything at some point. You can turn that one on with -XX plus use parallel GC. It's great for batch processing, or apps where throughput matters more than super fast responses. Then you've got CMS, the concurrent mark sweep. It's a bit more sophisticated. It tries to minimize those pauses by doing most of its work alongside your application, kind of like cleaning up while the party's still going on. But sometimes it can lead to fragmentation, and there might still be a few pauses. It's not perfect, and to be honest, it's kind of been replaced by G1 in a lot of cases. G1, that's garbage first. This one's really cool. It divides the heap into these regions and focuses on collecting the areas with the most garbage first. It's a good choice for large heaps, and when you've got a lot of objects coming and going, it tries to strike a balance between keeping things running smoothly and minimizing those pauses. And then, the really fancy one, ZGC. This is designed for those super low pause times, even with really massive heaps. So if you're building something huge and latency is super important, ZGC might be your best bet. You just use -XX. Plus, use ZGC to turn it on. Of course, there's always a trade-off, right? So with ZGC, you might sacrifice a tiny bit of throughput in some very specific cases, but it's all about understanding what your application needs and choosing the GC that fits best.
I like how you break it down into the use cases. That's really helpful. Now, we were talking about the heap earlier, and the sources also emphasize the difference between the heap and the stack. Knowing where different types of data live, that's pretty fundamental.
Absolutely, yeah. It's like knowing the layout of your house. The Java heap is where you dynamically allocate memory for all your objects. Think of it as the main storage space for all the data your program is working with. The stack, though, that's all about method execution. It's like a notepad for each thread. It holds those method-specific values, the local variables, and references to objects that are actually stored on the heap.
And our source has this little code snippet showing this. Using a string object and an integer array as examples, where would they actually end up in memory?
Okay, so imagine you've got the string hello. The actual letters, the H, the E, the L, those are stored on the heap. But the variable str, the one that points to this string that lives on the Java stack, it's associated with the thread running the code. Same deal with the array, like new and 10. The array itself is on the heap, and the variable array, well, that's just a reference to the array, sitting on the stack.
So the stack is basically holding pointers, like addresses, to the actual data which lives on the heap.
Yeah.
That separation is really important.
Oh, for sure. It's all about keeping things organized and efficient.
And speaking of keeping things organized, let's talk concurrency, another big one for senior Java developers.
Our sources jump into the Java memory model. They call it the JMM. So why is it so important?
The JMM, it's like the rulebook for how threads in Java interact with memory. It lays down the law for thread safety, making sure everything runs predictably. It covers things like visibility, atomicity, and ordering.
Hold on. Visibility, atomicity, ordering. Could you break those down a bit? Sure. So visibility, that's all about whether the changes made by one thread are actually seen by other threads. It's like, are they all on the same page? Atomicity, well, that's about whether an operation completes without any interruptions, kind of like doing something in one fell swoop. And ordering is about whether the sequence of operations appears consistent to all the threads involved, even though they might be running all over the place.
Right, because things can get really messy when multiple threads are accessing the same data.
Right.
So the JMM steps in and makes sure everyone's playing fair.
Exactly. It's like the referee in the multi-threaded game.
And to understand the JMM, we need to talk about working memory and main memory, right?
Yeah, that's where the action happens. Each thread has its own little workspace, its working memory. It's like a mini fridge where it keeps copies of variables it's using. These variables are actually stored in the main memory, which is like the shared pantry. This caching thing, it makes things faster, but you have to be careful or you'll end up with stale data. That's where our friends, synchronized and volatile, come in to save the day.
Ah, the trusty, synchronized, and volatile. Classic Java tools for thread safety.
They are. So, synchronized is like a bouncer at the club. It makes sure only one thread at a time can enter a critical section of code. This prevents race conditions and ensures memory visibility, meaning that changes made within a synchronized block are immediately visible to other threads.
So it's like putting up a do not disturb sign on a shared resource.
Exactly. And then there's volatile. It's more like a sticky note. It guarantees that every thread sees the most up-to-date value of a variable, but it doesn't provide that atomic guarantee for compound operations, just simple reads and writes.
Okay, and the source actually gives an example using a counter class, right? It has a count variable that's marked volatile and an increment method that's synchronized. How do these work together to make the counter thread safe?
So, marking the count variable as volatile ensures that every time a thread reads that value, it's getting the latest copy from main memory. No stale data here. And when a thread writes to the count variable, boom, The change is immediately sent back to main memory. Everyone's in sync. But there's a catch. The increment operation, even though it looks simple, is actually a read-modify-write sequence. A thread reads the value, increments it, then writes it back. Now, even with volatile, multiple threads could try to do this at the same time, and you might miss an increment. It's like two people trying to update the same whiteboard at the same time. Things get messy. That's why the increment method is also marked synchronized. The synchronized keyword acts like a mutex, making sure that only one thread can execute the increment method at a time. This guarantees that the increment operation happens atomically, and it also ensures memory visibility for the updated count value.
Okay, so volatile for single variable visibility, and synchronized for atomicity and more general visibility guarantees. I think I'm getting the hang of this.
You're getting it. It's all about choosing the right tool for the job.
So let's talk about actually running those tasks concurrently. Java gives us runnable and callable. What's the difference, and when would you use one versus the other?
So the big difference is what they can do. Runnable is for tasks that you just want to run, fire, and forget. It doesn't return a value, and it can't throw checked exceptions. Callable, though, it's a bit fancier. It can actually return a result, and it can throw checked exceptions, which is useful for error handling.
And the source has examples of both being used with executive service and future. Can you walk us through how these all fit together?
Sure, so the executive service is like the task manager. You can submit your tasks, both runnable and callable, to it, and it handles the execution. Now, when you submit a callable, the executive service gives you this thing called a future. It's like a receipt that promises you a result later. You can use this future to check if the task is done, to get the result when it's ready, and to handle any exceptions that might have happened along the way. The runnable example is pretty straightforward, just showing how to run a task. The callable example is a bit more interesting. It shows you how to use future.get to retrieve the result and how to handle any exceptions that might have been thrown by the callable.
That's neat. So callable gives you more control and flexibility when you need it.
Right. It's all about picking the right tool for the job, depending on what you need to accomplish.
Speaking of picking the right tool, a classic question in senior level interviews is about implementing a thread-safe singleton. Our sources cover 4 common ways to do this. Let's go through them one by one, starting with eager initialization, the simplest one.
Eager initialization, that's like preparing everything in advance. You create the singleton instance the moment the class gets loaded by the JVM. It's inherently thread-safe because the JVM takes care of all the synchronization during class loading. The code example shows this, with the instance being created right away as a static final field. And to prevent anyone from messing with the instance from outside, the constructor is private.
So it's always there, ready to go, but it might be using resources even if you don't need it.
That's where lazy initialization with double-checked locking comes in, right?
Yeah.
It tries to be a bit more efficient. Exactly. The idea with lazy initialization is to create the instance only when you actually need it. And this double-checked locking pattern, well, it first checks if the instance is null, but without any synchronization, to keep things light. If it is null, then it enters a synchronized block to double-check, and if it's still null, then it creates the instance. But there's a really important detail here, the volatile keyword. That's essential to make sure all the threads see the newly created instance. But, this pattern has had its issues, especially in older JVMs. There was this thing about instruction reordering during object creation that could cause some headaches, where one thread might see a partially created object. So even though it seems efficient, there are safer options out there.
Right, better to be safe than sorry. So let's move on to the next method, the initialization on demand holder idiom. This one sounds pretty clever.
Oh, it's a real neat trick. It takes advantage of how inner classes work. You see, inner classes, they don't get loaded until you actually use them. So when the singleton class is loaded, that inner singleton holder class, the one that actually holds the instance, it's just chilling. It only gets loaded when you call the getInstance method for the first time. And because class initialization is guaranteed to be thread safe by the JVM, the instance within that singleton holder, well, it's created only once and in a thread safe way, and only when you need it. This is generally considered the most reliable way to do lazy initialization.
Wow, that's pretty cool how it leverages the JVM's class loading mechanism for thread safety. And the last method we have is using an enum. This one seems surprisingly simple.
It is, and that's the beauty of it. Using an enum with a single instance is a super elegant way to create a thread-safe singleton. The JVM handles all the heavy lifting, guaranteeing that enum constants are initialized only once and are inherently thread-safe. Plus, it automatically deals with those pesky serialization and reflection issues that can sometimes cause problems for other singleton implementations. The example shows how simple it is, just a singleton enum with an instance.
That's really elegant. So we've covered a bunch of ways to handle concurrency and shared state. Now let's shift gears a bit and talk about exception handling. Another core Java concept. We know that Java has checked and unchecked exceptions. Can you explain the difference?
Sure. So checked exceptions, those are the ones that extend directly from the exception class, but not runtime exception. The compiler, that's like the rule enforcer, it forces you to either catch these checked exceptions in a try-catch block or declare them in the throws clause of your method signature. It's like a warning sign for the calling code saying, hey, this method might throw these exceptions, be prepared to handle them gracefully. Unchecked exceptions, though, those are a bit more wild. They extend from runtime exception or error. The compiler doesn't force you to handle these explicitly. They usually represent programming errors or those serious situations that are, well, usually not recoverable.
Got it. So checked exceptions, handle them or declare them. And unchecked exceptions, well, they're more likely to crash the party. But when should you actually consider creating your own custom exceptions?
Creating your own custom exceptions, it's like customizing your error messages. It's really valuable in a few specific situations, like when those standard exception types just don't cut it. They don't clearly describe the specific error within your app's context, or when you want to add some extra information to the exception, something specific to your domain. Like, let's say you have an insufficient funds exception. It might make sense to include the account number in the exception, or for a file not found exception, you might include the actual file name. Our sources have some examples of this. Another reason is if you want to create a whole hierarchy of custom exceptions. This helps you categorize errors within your system so you can handle them differently depending on the type. And custom exceptions also help distinguish your app's exceptions from those coming from external libraries, just to avoid any confusion.
And those examples really drive home the point that including specific context in your exceptions, that can make debugging so much easier.
Exactly. It's like leaving breadcrumbs for your future self or whoever else might have to maintain the code.
Speaking of making things easier, let's talk about try with resources. Java 7 introduced that, right? How does it help with exception handling, especially when we're working with resources like files or network connections?
Try with resources, it's like a built-in cleanup crew. It automatically manages those resources that implement the auto-closable interface. Think files, streams, network connections, database resources, all that good stuff. The best part, it guarantees those resources are closed properly. No matter what happens, whether there's an exception or not, they get closed. This means you don't have to write those tedious finally blocks just for cleanup anymore.
It's like magic. Things just clean themselves up.
Almost. And it gets better. It handles closing multiple resources in the correct order, the reverse of how you declared them. And it even manages those suppressed exceptions. If the closed method itself throws an exception while another exception is being handled. Our sources have some before and after examples with buffered reader and print writer. You can really see how much cleaner and safer the code gets with try with resources.
It's really neat how the language evolves to make things simpler and more robust. Now let's jump into some of the bigger features from Java 8 and beyond. Starting with Lambda expressions, those really brought a new style to Java. How do they actually work?
Lambda expressions, they're like those handy little functions you can pass around. They let you treat code as data. The compiler, it's like a mind reader. It figures out the types of your parameters and makes the syntax super concise.
Concise, yes, but they have some quirks,
Yeah.
right?
Well, they do have a few limitations. First, they only work with functional interfaces, those interfaces with just one abstract method. Then there's the whole thing about local variables. They can't access non-final or effectively final local variables from the surrounding scope. And exception handling can be a bit tricky. They can't directly throw checked exceptions unless the abstract method of the functional interface they implement declares it. And you can't overload methods based solely on the type of a Lambda expression. The source has a bunch of examples showing the basic syntax, parameterized lambdas, those block lambdas, method references. Those are a fun shorthand, and of course, that limitation with capturing non-final variables.
Ah, yes, those method references, another Java 8 gem. How do they relate to Lambda expressions?
Think of method references as shorthand for lambdas that just call an existing method. It's like, instead of writing a lambda that takes arguments and calls a method with those arguments, you just directly point to the method itself using this double colon syntax. So for example, system.out.println, that's a method reference that points to the printle method of the system.out object. It's the same as writing x-system.out.printlnx.
Right, like a shortcut, a way to say just use this method directly.
Exactly. It just makes the code a bit more concise and readable.
And then, of course, Lambdas open the door to the Stream API, probably the biggest game changer in Java 8. How's the Stream API different from the traditional way of working with collections?
The Stream API, it's a whole new way of thinking about collections. It's functional, it's declarative, there are a bunch of differences. First, streams, they don't actually store any data. They operate on a source, like a collection, and process elements one by one through a pipeline of operations. Think of it like an assembly line.
Makes sense. So it's more about processing than storing.
Right. And they're inherently functional, relying heavily on our friends, the Lambda expressions. And while collections are usually finite, streams can be, well, potentially unbounded. Fourth, you can only use a stream once. Once you've performed a terminal operation, the stream is closed, gone. And lastly, streams are lazy, and that means they only do the work when they absolutely have to, which can make them super efficient. Oh, and they make parallel processing a breeze.
So when would you choose to use the Stream API instead of just writing your own loops to work with collections?
You go with streams when you want to do those functional style operations, things like filtering, mapping, reducing data in collections. They really shine when you've got massive data sets where that lazy evaluation can really save you time and resources. Plus, they let you express those complex transformations in a way that's much more concise and readable. Like in that example, comparing the imperative and stream-based code for filtering employee objects. And don't forget about parallel processing. Streams make it so easy to split the work across multiple cores for a serious speed boost on the right tasks, like that example of counting high-earning employees.
That easy parallelization, that's a huge plus, especially when performance matters. Now, Java 8 also introduced default methods in interfaces. What problem did those solve?
Default methods, they were a real lifesaver for interface evolution. Before Java 8, interfaces were kind of stuck. They could only have abstract methods, no implementation. So if you wanted to add a new method, well, you break all the classes that implemented that interface. Default methods fix that. They let you add new methods with a default implementation right there in the interface. So existing classes didn't have to change a thing, but they could also override the default if they needed to. Like in that vehicle interface example with the turn on headlights default method, the car class, it can either use the default or define its own way to turn on the headlights. Static methods and interfaces, those are different. They belong to the interface itself, and you call them directly on the interface, like that is vehicle method. They're useful for those utility methods that make sense at the interface level.
So default methods bring flexibility and backward compatibility to the world of interfaces.
Exactly. It's like giving interfaces a power-up.
Let's finish up our core Java deep dive with reflection. What does Java reflection let us do exactly?
Java reflection, it's like having X-ray vision for your code. It allows you to look at and even change classes, interfaces, fields, and methods while your program is running without knowing about them beforehand. Pretty powerful stuff.
So you can actually inspect and modify your code at runtime?
Yep, that's the gist of it.
That sounds super useful. When would a senior developer actually use reflection?
Oh, it's used everywhere. Big frameworks like Spring and Hibernate, they rely on reflection for things like dependency injection and object relational mapping. IDEs, those tools we use to write code, they use reflection for code completion and refactoring. Test frameworks like JUnit, they need it to discover and run test methods. Serialization and deserialization processes, they often use reflection to check out the fields of an object. And like you see in the custom annotation processor example with @auditable, reflection allows you to examine annotations while the code is running and do stuff based on them. It's a fundamental building block for a ton of modern Java libraries and frameworks.
That annotation processing example, it's a really good way to see how reflection works. You're basically using metadata to control how your program behaves at runtime. Pretty neat.
It is. It's like giving your code the ability to understand itself.
Okay, we've covered a lot of ground with core Java. Let's shift our focus to object-oriented programming. Our sources highlight the solid principles as really important for good OOP design. Ready to tackle them one by one.
Let's do it. Solid principles, they're like the golden rules for writing clean, maintainable, object-oriented code.
All right, first up, the single responsibility principle. What's the main idea?
The single responsibility principle, or SRP, is all about focus. It says a class should have just one reason to change, basically one job and one job only. If a class is trying to juggle too many responsibilities, making changes becomes a nightmare. It's like having a chef who's also responsible for washing dishes and taking orders. Things are going to get messy. But if you stick to SRP, you get these nice cohesive classes that are easy to understand, test, and change without breaking everything else. The source has an example that shows this perfectly. The violates SRP example shows a user manager class doing way too much, like handling user persistence, email communication, and validation. 3 different jobs crammed into one class. Yikes. Then there's the follows SRP example, which breaks things down nicely into user repository, email service, and user validator, each focused on a single responsibility.
Right. Separation of concerns. It's like having dedicated specialists instead of one overworked generalist.
Exactly. Each class knows its role and does it well.
All right. Next up, the open-closed principle, or OCP. What's the gist of that one?
The OCP is all about being open to new things, but without messing with the old. It says that software entities, classes, modules, functions, should be open for extension but closed for modification. You should be able to add new features without changing the existing code, which is super important for stability. And we often achieve this with abstraction and polymorphism, like in that example with the payment processor. The violates OCP example has this payment processor with a ton of if-else statements for handling different payment types. Adding a new payment type means changing that core class, which is risky. But the follows OCP example does it the smart way. It introduces a payment method interface, and each payment type gets its own implementation. So to add a new payment method, you just create a new class implementing that interface. The payment processor itself doesn't have to change, which is exactly what we want.
That's the beauty of interfaces. You're programming to an interface, not to a specific implementation.
Exactly. It's all about flexibility and future-proofing your code.
Okay. Third on the list, the Liskov substitution principle. This one's a bit more subtle.
It is, yeah. The LSP, it's about making sure that subtypes play nicely with their base types. It says that you should be able to swap a base class with any of its subtypes without causing any weird behavior or breaking things. It's all about maintaining that is a relationship in a robust way. Like imagine you have a rectangle class and a square class, and square inherits from rectangle. Seems logical, right?
Yeah, a square is a type of rectangle.
Exactly. But the LSP points out a potential issue here. If you set the width of a square, you'd also expect its height to change to match, right? But code working with a rectangle might assume you can change the width and height independently, and that can cause problems when you use a square instead. The follows LSP example tackles this by using a more general shape interface with a getArea method. Both rectangle and square implement it, so they adhere to a consistent contract.
I see. So the subclass needs to truly honor the contract of its superclass. Makes sense.
Right. It's all about making sure that inheritance doesn't lead to unexpected behavior.
Fourth principle, the interface segregation principle.
The ISP is all about keeping interfaces lean and mean. It says clients shouldn't be forced to depend on interfaces they don't use. Think about it. If you have these huge interfaces with tons of methods, the classes implementing them might end up having to implement methods they don't even need, which just bloats the code and makes it harder to maintain. It's like buying a whole toolbox when all you need is a screwdriver.
Right. Why pay for what you don't use?
Exactly. The source have a classic example, the worker interface. The violates ISP example shows a worker interface with all sorts of methods like work, eat, and sleep. Now, a robot worker, it might need to work, but it definitely doesn't need to eat or sleep. So the follows ISP example breaks down this big worker interface into smaller, more specific interfaces like workable, eatable, and sleepable. This way, classes can implement only the interfaces that make sense for them, leading to much cleaner and more focused code.
More modular and less clutter. I like it. And finally, the dependency inversion principle.
The DIP, it's all about inverting those dependencies to make your code more flexible and easier to test. It says high-level modules shouldn't rely on low-level modules directly. Both should depend on abstractions. This reduces the coupling between different parts of your system, making it easier to change one part without breaking another. It's all about decoupling.
Right, decoupling. That's always a good thing.
It is. And the source is a simple example to illustrate this, the switch and light bulb example. The violates DIP version has the switch class directly tied to a specific light bulb class. So if you want to control a fan instead of a light bulb, you have to change the switch class, which isn't ideal. But the follows DIP version introduces a switchable interface. Both light bulb and fan implement this interface, and now the switch depends on this abstraction, this switchable interface, rather than concrete implementations. So the switch can control anything that's switchable, making it much more flexible and reusable.
I see.